My name is Rheinländer. Thank you for the introduction. I am here with the Microelectronic Systems Design Research Group from the University of Kaiserslautern in Germany. Today I'm going to talk to you about timestamp generation for synchronization in Bluetooth low energy networks. Nowadays, wearable devices are a growing industry field. A sensor device run on human body, measures parameters like the heart rate and
so this is a wearable device too, right? Kind of. It's better, you know? Okay, so this data is sent to the smartphone, and on the smartphone we have, for instance, a fitness app that analyzes the data and gives us feedback about our workout performance. In order to have a good battery lifetime here and to be compatible to every smartphone, the wireless technology used here is Bluetooth Low Energy, or also known as Bluetooth Smart. But wearables can do more than that. For instance, if we look at high-performance sports, the precise movement analysis of an athlete is a growing industry field, research field in sports science. The reason for that is that it's possible to early detect possible injuries due to faults carrying out of the exercises. And by digitally assisting the coach, the performance of the athlete can be done way better than just by observing. So one way we can do that is to attach various sensors on the athlete's body to electronically reconstruct his movements. A big challenge that comes with multiple distributed sensors is that the data they produce has to be properly synchronized. Depending on the application case in sports science, the requirements for the synchronization are in the way below the millisecond range. So far so good. Wireless synchronization has been a wide research field and has been explored a lot. But if we use Bluetooth Low Energy as a wireless communication technology, synchronization will suffer from a problem called nondeterministic delays that appear in the Bluetooth Low Energy stack. Now, what does that mean? In order to understand this problem, we have to look into more detail of a Bluetooth Low Energy connection. Here we have two devices that want to communicate with each other. In order to establish a connection, the central device sends a connection request to the peripheral device. After that, the connection is established and both devices exchange data. This is called a connection event, and it takes about 3 milliseconds. After this connection event, both devices go to low power sleep mode to preserve energy. They both independently wake up after a certain time period called connection interval, and then a new connection event takes place. If we look at the Bluetooth Low Energy stack, this entire process is controlled in the link layer. And it's important to know that these consecutive connection events will take place all the time, even though no data is to be sent. It's to hold the connection. So how does it work if we want to send data from the application? The application forwards the data to the Bluetooth Low Energy stack, and the stack takes care that the data is transferred during the next consecutive connection event. The problem here is that the application never really knows when exactly the data is physically transferred. And that's what we call the non-deterministic delays between those two layers. So synchronization protocol implementations in the application layer will suffer from this non-deterministic delays and deliver bad results. As we can see in related work, they applied pairwise broadcast synchronization to Bluetooth Low Energy, and we can see the results are not that good because this application suffered from those non-deterministic delays. Another idea was that delivered better results was to use common events into interconnected devices. The disadvantage of that approach was that the application is quite restricted because we need things like frequent reconnects. So there was even a third idea that delivered very good results, But in order to do that, they had to implement their own proprietary Bluetooth Low Energy stack, which means they functionally used a standard Bluetooth Low Energy stack and added link layer timestamping to the stack to achieve these good results. As we can see, all these related work have drawbacks. It's either poor results or restrictions in the application, or we even have to use non-standard stacks to get good results. So we were thinking, how can we come over these drawbacks and still have a good synchronization accuracy? So what related work basically did, they used a software-based approach to somehow inform the application about the link layer activity. Our idea was different. Our idea was to come up with a hardware-software combination approach, which means we included the physical layer into our design. In order to observe the activity on the physical layer and forward it to the application, we used the power consumption of the Bluetooth Low Energy chip. In order to do that, we placed a shunt resistor in the voltage supply path of the Bluetooth Low Energy chips. And here we can see a measurement during the connection interval of measured with an oscilloscope. Let's look into more detail here. So in the beginning, both devices sleep. The current consumption is about a couple microamps. Here, both devices wake up and start their high-frequency oscillators. The two high peaks in the end are caused by the radio peripheral. So we can see that the radio actually has a very high impact on the overall current consumption of a Bluetooth Low Energy chip. In order to use this characteristic as a source of timestamping, we simply amplified the voltage over the shunt resistor and forwarded it to a comparator input of the chip. We then experimentally defined a threshold and configured the comparator to fire a hardware interrupt every time this threshold is exceeded. In order to examine the possible synchronization accuracy that we can achieve by using these interrupts as timestamps for synchronization, we measured the time difference between those two interrupts appear on in two connected devices. In order to get good results, we measured 5,000 connection events for each setup. Each setup means we also wanted to find out the impact of connection parameters like the connection interval. That's why we tested 9 different connection intervals. We furthermore tested 6 different oscillators with different accuracies. These are the oscillators that control the link layer activity, like the frequently wake up. So it's a very important parameter here. And here's the results. As we can see, the frequency distribution doesn't depend on any of the parameters. That's because we used the falling edge, like when the radio communication is over, as source of the interrupts. And the standard deviation is very low. It's below 1 microsecond. So by using a standard Bluetooth Low Energy chip, a conventional one for just $3 or $2, and a minimum set of external components, we achieved the best known synchronization accuracy based on the standard deviation for Bluetooth Low Energy. Thank you.